Hello, fellow investors and friends of Delta Resources. This is Henri Tessier, your president and CEO. This month, we decided to mix it up somewhat with this president's message and use this platform to better explain our press release of February the 18th, 2020. In that press release, we announced the completion of our helicopter-borne VTEM geophysical survey over our Delta 2 property in Chibougamau, Quebec. In this video, I'll be providing some more details about the survey and why we think the results are very exciting. The complete video is less than 15 minutes, but if you're already well versed in geophysics, you can probably skip to slide 9 where I discuss the project and the results. The first part of the presentation is more of an introduction to these geophysical methods. Before we get going, please read through our forward-looking statement when you get a chance to better put into context the statement I'll be making during the presentation. I also need to let you know that I'm a qualified person under the rules of National Instrument 43-101. So let's get going. During this presentation, in addition to geological maps, I'll be showing geophysical magnetic maps and geophysical electromagnetic maps. This one is a magnetic map of the property. Magnetic surveys detect the magnetism of rocks. There's only a few minerals that are magnetic, but the main ones are magnetite and sometimes pyrrhotite. So essentially, the magnetic survey gives us an idea of the magnetite content of rocks. Needless to say, these surveys are very sophisticated and sensitive. On this map, the rocks that are magnetic show in the warm colors, like the yellows, the pinks, and the red, while the rocks that are less magnetic show in the cool colors, like the blues and the greens. Typically, mafic rocks will show as magnetic, while more felsic rocks are not. And of course, the whole range also exists in between. We use these magnetic maps to help with geological mapping in areas particularly where the surface exposure is scarce. Disruption in a magnetic trend, for example, can indicate a fault, and certain magnetic signatures can indicate certain types of rocks. For example, the contrast between the green and the light blue indicates that this area here is a more felsic intrusion called tonalite. Let's take a look at an electromagnetic map of the property. Here, the geophysical method indicates the conductivity of the rocks, or the ability of the rocks to conduct an electrical current. Rocks, or minerals, that are particularly conductive include graphite, and more important to us, sulfides, such as pyrite, pyrrhotite, chalcopyrite, pentlandite, and other sulfides. For a rock to be conductive, these conductive minerals need to be interconnected into a certain mass. A good conductor will have great conductivity between those minerals, and a poor conductor will have less conductivity. If there's no conductivity, what we call disseminated mineralization, then the rock will not show as a conductor. This is particularly important to us because we're looking for volcanogenic massive sulfide deposits which concentrate sulfide minerals such as pyrite, pyrrhotite, chalcopyrite into masses that are typically good conductors. To note, zinc-rich VMS deposits don't necessarily show up as a good conductor because their main mineral is sphalerite, which is not conductive. That said, the sphalerite is typically associated with other conductive minerals like sulfides. On this conductivity map, the reds and the pinks are conductive rocks, while the yellows are not conductive. On maps, we represent these conductors as large dots, such as here. The circles are positioned where the conductors are located. So each dot corresponds to where a flight line crossed over a conductor. So when you have the dots lining up, like here, for example, it just means that the conductor spans over several flight lines. A circle that is completely black, like these guys here, is a good conductor, while a circle that is not filled in is a poor conductor. And those filled halfway are medium conductors. One thing that's also important to discuss is the distinction between what we call formational conductors and isolated conductors. On this map, the dots that are pointing to the conductors are superposed on a magnetic map. We often do this so we get the benefit of both types of surveys. Formational conductors usually show up as strings of conductors that extend for a long distance, up to hundreds of kilometers, just like this conductor right here, for example. These long conductive horizons correspond to conductive rocks or rock formations, or sometimes graphitic faults. Those conductors are very long and of lesser interest. We don't often see VMS deposits that are 100 kilometers long. Not to say that a punctual VMS can't hide in there, but typically they don't. What we're looking for as a volcanogenic massive sulfide deposit signature are conductors that are relatively punctual, with lengths of 1 to 10 flight lines, for example, if the lines are spaced at 100 meters. As VMS deposits have limited strike length. If we combine the electromagnetic signature with the magnetic signature, many geologists and geophysicists like the association of a conductor with a magnetite high, magnetic high, because VMS deposits often have pyrrhotite. And this would be an example of one right here. So it's relatively punctual, about 1 kilometer in strike length, and associated with a mag high. Now, historically, the government provides magnetic and sometimes electromagnetic maps of certain areas. Also, companies have historically carried out similar surveys, and their data is held within government databases, also available to us. So why do we still carry out these surveys? Well, there's several reasons. Like any technology, it has improved tremendously with time. The instruments are more powerful and more sensitive so that we can see more clearly and deeper. The geopositioning of the anomalies is also much better than it used to be, so much so that we can now drill targets directly from these airborne surveys. Finally, the government geophysical surveys are relatively low resolution because of the wide spacing between flight lines. Obviously, the closer the flight lines, the better the resolution, and we flew at 100-meter spacing. So this image here shows you the difference between a government magnetic survey down here versus our new VTEM surveys over here. You can see that we get much more detail with our new survey, and that helps us better define the geology and potentially pinpoint new targets. Note here that this map is an amalgamation of several geophysical surveys. This one here outlines our survey from 2020, and these other two surveys were carried out in 2012 by other companies. The low resolution background is from government surveys, so all these maps were merged together. This image here shows you the difference between a government electromagnetic survey and our new VTEM survey. You've guessed it, the EM in VTEM stands for electromagnetic. What this map shows are the dots that are representing conductors, again, over the magnetic background. If we zoom in onto this area here, what we see are the red dots and the gray dots that are from former surveys, while the black dots are from our new geophysical VTEM survey. You can see that there are many more anomalies with the VTEM survey than in the previous surveys, and that's because of the increased sensitivity of the method and because it penetrates deeper. So now that you have the background, let's look at our results at delta 2. For those who don't know the Delta 2 property, it's located 35 kilometers southeast of Chibougamau, of the Chibougamau mining camp, with easy access via paved Highway 167. It's a very large property, covering now over 135 square kilometers. The geology of the property consists of two volcanic cycles, one in dark green at the base and the other one in light green at the top. Both are intruded to the south by a synvolcanic intrusion called the La Dauversière intrusion, which is of similar age and similar composition as the Chibougamau pluton, which is responsible for all of the copper-gold mineralization of the Chibougamau mining camp. The generally east-west lines are early faults, and the faults in dotted line like this are actually later faults. There's great potential for Delta 2 for gold deposits related to the pluton, just like the Chevrier deposit that occurs a bit further to the west, and the R14 deposit on our property right here. But for the sake of this presentation, we'll discuss the great potential for gold-rich volcanogenic massive sulfide deposits along this contact between the two volcanic cycles. Here, I've outlined the contact in white, and the exact same white contact will appear on the next map. So this very same contact is now shown on the magnetic map. And what we can see is that in the western part of the property, the contact is fairly well defined by a contact between magnetically fairly high rocks and magnetically fairly low rocks. There's a slight discrepancy, but this can be corrected just like so. In the eastern portion of the property, it becomes apparent, though, that the contact is much more complicated, and we can see a disconnect between the interpreted contact and the magnetic signature. Now, this is how our geological team interprets the position of the contact with our new high-resolution survey. What we can see is that there's very large folds in the eastern part of the property, one located here and another one located here. The discrepancy between the two interpretations probably stems from the difficulty of access in that area at the time the government geologists mapped the area in 1989 and 2004, some 30 and 16 years ago. The area has since been logged and is much more readily accessible. Now, if we zoom in onto this area, we'll show you why we're so excited about this new survey and the new anomalies. So this is zooming into our new interpretation. What I've done here is I've reduced the size of the hashed line that shows the contact, the important contact, just so that we could see the anomalies better. What we have here are basically the conductors over the magnetic map. And what we can see here is that we at least have 10 high priority targets. All are brand new. They've never been drilled. They are good to moderate conductors. They're all associated with mag highs. Remember the association with pyrrhotite here. All are of limited strike length, so they're not formational. They're all in proximity to the favorable VMS contact, and at least 3 are associated with a zone of garnet chlorite alteration defined by Delta in the fall of 2019. The type of alteration that's often seen in the footwall of VMS deposits. And we also have many anomalies in the western part of the property here that remain to be evaluated. So you can see why we're excited, and we're looking forward to testing these new targets. So what's next at Delta 2? Well, we have a 3-pronged approach. First, we want to fly the southwest portion of the property with a high-resolution magnetic survey to outline gold-bearing structures. Then we want to initiate fieldwork as early as April 2020 to field-proof geophysical anomalies and expand new gold occurrences. Then we definitely want to drill test these new anomalies. Thanks very much for tuning in. As always, don't be afraid to contact us or visit our website at www.deltaresources.ca. We're more than happy to answer your question. This is André Tessier on behalf of the whole Delta Force. Until next time.